Hi guys, in today's video we are going to derive D'Alembert's formula for the wave equation using the Fourier transform. Recall that D'Alembert's formula is precisely the solution to the wave IVP with initial displacement phi and velocity psi on the real line. But before we begin, let's go over some helpful tools that will assist us in the derivation. First, let's consider the Fourier transform itself. Recall that the Fourier transform function f of x is simply the integral going from negative infinity to infinity of the function f of x times e to the minus ikx dx. And we can write this as a shorthand simply as f hat of k, where k is a real number. And remember that the transform really takes a signal and expresses it in terms of the frequencies of the waves that it makes up the signal. So we have the Fourier transform, but we also need to know what happens when we take spatial derivatives and time derivatives. What will happen then? Well, as it turns out, taking derivatives with respect to time of the spatial derivative of a transform function will simply be the transform function, but in front there will be a factor of ik to the nth power for each derivative times the transform function itself. So that will be helpful because in the wave equation we do have uxx term. So two spatial derivatives taken at the same time. So if the spatial derivatives, how about the temporal derivatives? If we take into account temporal derivatives, notice that the Fourier transform does not do anything with the temporal derivative or temporal variable at all. There's no t's in the Fourier transform. So the nth derivative with respect to t of a transform function, this will be the integral of minus infinity to infinity of the derivative Tn f of x e to the minus x dx. And it turns out that the differential commutes, the t derivatives commute with the transform. So we can pull it outside and change it into a partial derivative. So dn, dtn, dx, e to the minus ikx dx. But this integral is simply just the transform function of f, which is simply just partial n, partial t to the n of f hat of k. Alright, so we have the spatial and temporal derivatives of a transform function, but it would also be helpful to recall Euler's formula as well. So remember, Euler's formula e to the ix is simply cosine x plus I sine x. And from this, we really want to focus in on the complex definitions of cosine and sine, being cosine x is equal to e to the ix plus e to the minus ix over 2, and sine x being e to the ix minus e to the minus ix over 2i. Alright, with that being said, I believe we can get started on the derivation. So to get started, let's Fourier transform the problem. So the problem here, we're going to call it star. We're going to transform the equation and the auxiliary conditions as well. If we do so, using the two observations we noticed about temporal and spatial derivatives of a transform function, utt and uxx, we're going to transform to u hat kt, so x transform into k. So we will get that u hat taken to the time derivative twice minus c squared times ik squared of u hat. And the transform of 0 is simply 0. The auxiliary conditions will become u hat of k0 is equal to phi hat of k, and u hat time derivative k0 is equal to psi of k, psi hat of k. All right, but this I squared will change this minus the c squared to a positive c squared k squared. So we can rewrite this as u hat tt plus c squared k squared u hat is equal to 0. But notice, we have just time derivatives here. There are no more spatial derivatives. So if we make a clever substitution by letting u hat of kt be equal to some f of t, for example, star becomes f of t, f double prime of t, plus c squared k squared of f of t is equal to 0. The initial displacement becomes f of 0 is equal to phi hat of k, and the initial velocity will be f prime of 0 is equal to psi hat of k. And this is simply just a second order differential equation, and it's also homogeneous, so we can use the fundamental set from our basic differential equations course and other techniques to help us solve this. So, pulling out the characteristic equation of this differential equation, it's going to be m squared plus c squared k squared is equal to 0, which implies that m is equal to plus or minus cky, and by our knowledge from differential equations, the general solution of this will be f of t equals to a cosine of ckt plus b sine ckt. And of course we can find a and b, these are constants, because we have two auxiliary conditions. Doing so, we put in f of 0 to be equal to phi hat of k. We'll get that a, cosine of 0 is just 1. The b term vanishes because sine of 0 is 0. A is equal to phi hat of k. So that is 1 constant. If we differentiate f of t, we will get a, or minus a, sine ckt. By the chain rule, we have to multiply by the derivative of the inside, so that's ck, plus b ck cosine ckt. This is equal to psi hat of k. So that means if we put 0 in for t, the first term vanishes, sine of 0 is 0. The second term, we will have bck is equal to psi hat of k. But then this implies that b is just psi hat of k over ck. Putting it all together, the particular solution will be f of t equals psi hat, or phi hat of k times cosine ct plus psi hat of k over ck sine ckt. Alright, so yes, we solved the differential equation, but let's see where we got this. What is f of t really? F of t, remember we said f of t was u hat of kt, the solution of this this problem right here, the transformed star. But in order to get the solution of our original problem star, we would have to take the inverse transform of f of t, such that u of xt will be the inverse transform. So the inverse transform is 1 over 2 pi of integral going from the reals of f of uxt, so ukt actually, ukt e to the ikx dk. So this we would put in u hat, which would then be 1 over 2 pi integral going over the reals, so the reals is negative infinity to infinity, of this f of t that we found, because f of t equals u hat. So psi k cosine ckt plus psi hat of k over ck sine ckt. We gotta put these in brackets because we're multiplying by a factor of e to the ikx dk. Alright. So normally, solving PDEs using the Fourier transform, you're going to end up with this pseudo answer. You're just going to end up with an impossible integral to solve. But luckily in this case, we can use Euler's formula to help us simplify down these integral into two integrals, solve them separately, and eventually reach D'Alembert's formula. So let's go ahead and try to do that. By the linearity property of the integral, we can split up the integral into two integrals from this sum. Doing so, we will get the integral going over the reals of the first integral, cosine ckt, multiplied by a factor of e to the ikx dk, plus 1 over 2 pi, integral going over the reals, of psi hat of k over ck times sine of ckt times a factor of e to the ikx dk. Alright, so now we've hit a stopping point, but let's utilize the last item in our toolbox, which is to we use the complex definitions of sine and cosine to help us degenerate our integral down to something more solvable. So doing so, we replace cosine and sine with their exponential definitions. We get that cosine of ckt is nothing but e to the ickt plus e to the minus ickt over 2 and sine is really just e to the ickt minus e to the minus ickt over 2i, and there we go. Now from this point on, why don't we just call this first integral I1 and this second integral I2, and have it that the solution of the original problem star is simply just I1 plus I2. So let's go ahead with I1. I1. The I1 is 2 pi. Why don't we multiply in this factor and combine using your exponent rules? So we'll take 1 over 2 pi, and we'll also bring out this 2 as well from right here. Integral going over the reals of phi hat of k times e to the I ct plus x ikx plus phi hat of k of e to the I ct minus ct plus ikx dk. By the linearity property, we can split this up into two integrals. So the first integral will be the first term in the sum, and we'll factor out an ik from the exponent, so we can rewrite this as ik, e to the ik, times x plus ct. This will be with respect to k. And the second integral will be 1 over 2 pi going over the reals of phi hat of k, ik, we'll put the x out in front, x minus ct dk. And all of this is a factor of 1/2 on the outside. All right. So what can we see? Well, recall that the Fourier transform of f of x is 1 over, or is the integral. Wait, no, my bad. That the inverse of the Fourier transform of x going backwards is really 1 over 2 pi integral going to the reals of the transform function times e to the kx dk, where the input matches this x right here. The input x matches with this input. Notice that we have x plus ct where x usually is. X plus ct over here and x minus ct over here. If we replace this with phi and reimagine it a little bit, it should be really clear what we see. And we see precisely that this first integral evaluates to phi of x plus ct. And the second integral evaluates to phi of x minus ct, giving us the first part of D'Alembert's formula. All right. Now how about the second integral? The second integral is the same thing, or not the same thing, but a similar thing. So we have 1 over 2 times 2 pi, integral is going over the reals of psi hat k over ck times e to the ik x plus ct minus e to the minus ik x minus ct over 2i, or just over I here, dk. Again, by the linearity rule, we have that we can split up these integrals into two with the sum. We have, well, hold on. We have this I term out in front as well. So 2 times 2 pi, and this I term out in front of, so, well, hold on, let's take it from the top actually. We have this I term, we can't really take it out, but here, why don't we just try to make a substitution. Because this I term, we can't really proceed here. We don't really know how to integrate with this. So why don't we create a substitution? We'll let psi x be equal to psi of SDS. We'll integrate this from a to x, such that if we take the derivative with respect to x, we'll get that psi prime of x is simply just psi of x, our original thing. But now what we want to do is we want to Fourier transform this, both sides. Doing so, we get ik times psi of k is equal to psi hat of k, or in other words, psi hat of k is equal to psi hat of k over ik. Okay, which is good because we have this I on the denominator. We have an I on the denominator here. We also have a K on the denominator as well. So all of this really means that if we substitute this into I2 is then equal to 1/2 times 2 pi. Integral going over the reals of simply psi hat of k. And we'll pull out the c as well. We'll put the c right here. Of e to the ikx plus ct minus e to the minus ikx x minus ct dk. And if we pull this out, we can use our similar logic up here and eventually reach the fact that this is really equal to 1 over 2c of psi x plus ct minus psi x minus ct. But what is psi really? Psi is really just the integral of psi SDS going from a to x. So we have our inputs here. We put our inputs in correctly. This is really the integral from a to x plus ct of psi SDS minus the integral from a to x minus ct of psi s ds. But this is really equal to, well, the second integral can be rewritten if we flip the bounds by simply just introducing another negative. This negative changes to a plus, and we get that x minus ct goes to a of psi s ds. And we have an integral from a to x plus ct, and an integral from x minus ct to a. So those a's will cancel if we take the primitive of them anyways, so we can simply combine this into one single integral from x minus ct to x plus ct of psi s ds, where s is simply just a dummy variable. And this is equal to I2. And thus, we'll have that u of xt is I1 plus I2. Or in other words, D'Alembert's formula. 1/2 phi of x plus ct plus phi of x minus ct plus 1 over 2c integral from x plus or x minus ct to x plus ct of psi s ds, which is exactly what we wanted to show. And that would be a good stopping point.